Without further ado, please welcome with a warm round of applause, Professor Walter Lewis.
A measurement without knowledge of its uncertainty is not very meaningful. This is so key in experimental physics, and yet it is not covered in high school physics, and it is not covered in any college physics books. But it is so important that I want to repeat this statement. A measurement without knowledge of its uncertainty is meaningless. And I'll give you an example. When I was a kid, my grandmother said, do you know when you lie down that you're taller than when you stand straight up? Puzzled me. We couldn't confirm it in any way. We didn't have the means to do that. But it haunted me for years until I came to MIT and I decided to bring it to a test. I reasoned as follows. It couldn't be that when you jump out of bed, that you all of a sudden become 10 centimeters shorter. You would know that. You would get out of bed and you go clunk, you would know that. So it couldn't be 10 centimeters. I also reasoned if my grandmother is right, it couldn't be 1 millimeter because you would never know. So if she is right, it's probably a centimeter, maybe a little more, maybe a little less. So if you want to measure it to see whether it's really true, the accuracy of your measurement, which physicists call uncertainty, the uncertainty of your measurement would have to be about 1 millimeter. And I want to bring that to a test today. I have here an aluminum rod, and I'm going to measure this aluminum rod, its length, in vertical position and in horizontal position. I think none of you would believe that the rod would become longer if it is horizontal, so that's not an issue. But I want to prove to you also that I can measure the length of that rod to an accuracy of about 1 millimeter, which was my goal. And so I need someone to help me who is capable of reading metric system, who can read millimeters. I don't want to hear about inches and feet. That drives me nuts. Who can read? Can you read millimeters? Could you please come? I'm Walter Lewis.
I'm Adrian.
And what is your name?
Adrian.
David?
Adrian.
Adrian, if you stand on this side, here we have the aluminum rod, and we're going to measure the length of this aluminum rod in vertical position. Do the best you can, and try to get it as accurate if you can to 1 millimeter.
149.9.
I agree with you. 149.9. No, don't go away. So, in vertical position, the aluminum in vertical position is 149.9. Plus or minus 1 millimeter, maybe. Could we agree on that? Plus or minus 1 millimeter. So plus or minus 0.1 centimeter. So now if you come on this side, we're going to measure this aluminum rod in the horizontal direction. And I want you to do the reading so that we're all sure that it's done in a scientific manner. Okay. Could you read?
Yeah, it's, wait, what?
148.9? That, yeah? That's hard to believe. I thought you told me that you know how to read metric systems.
149.85.
149.85. Boy, you're accurate. Don't go away. 149, did you say 0.85? I still think we should allow for the uncertainty of about 1 millimeter. I have convinced you now that I can indeed measure to an accuracy of roughly 1 millimeter, and I've also convinced you that the vertical setup and the horizontal setup are both kosher, because they give the same result. So now, Adrian is your name, now we need a candidate whom we're going to measure vertically and whom we're going to put to sleep and measure horizontally. And I would like someone who is reasonably tall, because I argue that the taller person, the difference between standing and lying will probably be larger than the small person. But the person cannot be this tall, because then I can't measure it. So who would want to volunteer? Who is somewhere around 6 feet, who is willing, for the sake of science, a little sacrifice? Would you like to try that? I see the smile on your face. You'd love to do it, right? Okay, come on. You're a bit on the short side. Well, we'll accept you anyhow. Oh, you have to take your shoes off. Now, why do you have to take your shoes off, you think?
Because they add height.
What?
They add height.
Well, but you go horizontal, you go vertical. Why is it important to take your shoes off?
Because they compress when I...
Ah, you're good! Because when you stand up vertically, maybe you compress them. We don't want that, so take your shoes off. Very good. What is your name?
Tiffany.
Tiffany.
Yes.
Okay, stand here, and you are the man who knows how to read metric systems, right? So, make sure your feet are against the back. Yeah? Are you nervous?
No.
You should be.
Will be 164.8.
164.8. Stay here. What was your name?
Tiffany.
That's too difficult. Person. Vertical. What is the, what was the reading? You've forgotten already.
Wait, what? 0.9? No? 0.6? Oh,
What?
now it's 0.8.
Now, you see, the 1 millimeter uncertainty is not unreasonable. What do you want?
164.8.
1.8. Okay, now, may I invite you on the table? And I'd like your feet there. And lie down and relax. Feet all the way against there. And relax, we don't need the aluminum bar anymore. Adrian, make sure that you agree with the way that I do this. Your hand a little bit in. Yeah. Okay. So we move this in again. Adrian, can you do the reading?
That can't be right. This one's 66.
Point
Zero.
point zero. Just relax, stay there, yeah? Horizontal, 166.0 plus or minus 0.1 centimeter. It's a little more than 1 centimeter. My grandmother was right. Thank you very much. You can go back to your seat. I hope you have now understood the importance of knowing the uncertainty in your measurement. Because if the uncertainty that I had was way larger than 1 millimeter, you would never know. Now, this result is not surprising, because when you're standing, gravity compresses the soft tissue between your vertebrae of your spines. Thus, when you lie down, our spines expand. This may seem obvious to you now that you know it. However, would you really have predicted this? In fact, not even the scientists at NASA anticipated this effect in planning for the first space missions. And then the astronauts began to complain, all of them, that their suits were too tight. And then later on in the program, tests were made, and it turned out that after 2 days of weightlessness, that someone who was 6 feet tall would grow 5 centimeters. And so therefore the suits that NASA built were, of course, correcting for that, allowed for this growth. I'm now going to tell you more about gravity. I know you're the general public, you're not MIT students, so don't get nervous yet. I will take it very easy today and make it a little harder on Friday. If I drop an object, just drop it. Just let it go. Then it will start to go down to gravity. And then after 1 second, it has a speed of 9.8 meters per second. And after 2 seconds, it had twice that, so it has a speed of 19.6 meters per second. And after 3 seconds, it has the speed of 3 times that, which is 29.4 meters per second. And after t seconds, it has a speed of 9.8 times t meters per second. So every second, the speed increases by 9.8 meters per second. And we physicists have given this a name. We call that G. We call that the gravitational acceleration due to the Earth. G is not everywhere on Earth exactly the same, but very closely the same. And in 26/100, it is very close to 9.80. Now think about it. So every second, the speed increases by 9.8 meters per second. So it is 9.8 meters per second for every second. That's why physicists call this simply 9.80 meters per second squared. And if it's difficult for you to swallow the idea that we have meters per second square, well, you will get over that. But that's really what it is. It is a change of speed per second, and therefore it is meters per second square. The gravitational attraction of the moon is 6 times smaller, and the gravitational attraction of the sun is 28 times larger. I now would like to make a plot for you of the velocity, if you want to call it speed, I have no problem with that, as a function of time. So we drop an object, and we drop it with 0 speed. Here we plot the velocity in meters per second, and here we plot the time in seconds. And when we do that, we get something like this. You get a line like this. After 1 second, this is 9.8 meters per second. Here's a 0. Remember, we dropped it with 0 speed. After 2 seconds, it is 19.6 meters per second. And after 3 seconds, 29.4. So what I have plotted for you is really the relationship that the velocity v equals g times t, the g being the 9.80. And if t is 0, then v is 0. If t is 1, then v is 9.8. And if t is 2, then it is 19.6. And that's the way we can represent that in a very easy way, algebraic way. Galileo Galilei has been credited with throwing objects from the Tower of Pisa of different weight. Whether he ever did that or not is very questionable, by the way. But at least he drew the right conclusion. And that conclusion was that it doesn't matter how much it weighs. All these objects, if you drop them from the same height, will reach the ground with exactly the same speed and therefore also with exactly the same time. So each one of them will obey this law regardless of how much it weighs. I'd like to demonstrate that to you, that indeed it is remarkable that objects of very different weight fall with the same speed and hit the floor at the same time. I have here a golf ball, and I have here a bag of sand, which weighs at least 50 times more than the golf ball. And I'm going to drop them from the same height. So we are doing a post-Galileo Galilei experiment. And I hope you will be able to see that they both reach the floor at the same time. 3, 2, 1, 0. As close as you can get to the same time. But now, thank you, Anna. But now, I wonder if Galileo Galilei was right. If it doesn't matter how much something weighs, it should also work for a feather and a basketball or a baseball. And so, I have here a feather, and I have here a baseball. And wouldn't it be nice if indeed they both hit the ground at the same time? But what do you think will happen? They won't. And why will they not? Air drag. There is air resistance. And that we have not taken into account at all in my calculations here. Clearly, the air drag on the feather will be enormous in comparison with the baseball. So I would expect that Galileo Galilei was not right when it comes to feathers because of the air drag. 3, 2, 1, 0. Huge difference in time. Now, in order to do justice to Galileo Galilei, who clearly had the right idea, and he realized himself, of course, that you cannot do that with feathers. In order to do justice to this great scientist, in 1971, the astronaut David Scott, who was on Apollo 15, was on the moon. And there is no atmosphere on the moon, so there is no air drag. And he had a feather and a hammer, and he had them both 1.6 meters above the ground, and he dropped them simultaneously, and indeed, the feather and the hammer hit the surface of the moon at the same time. You may think, since the gravitational attraction of the moon is 6 times lower than the Earth, you may think that it took 6 times longer for the objects to fall than on Earth. If you think that, that's wrong. You may think that maybe the speed with which it hits the moon is 6 times lower, because after all, v is gt, and if g is 6 times lower, v better be 6 times lower. Also wrong. And I will tell you next time why that is wrong. But I do want to show you the video that was made on the moon. It's very poor quality. And you cannot understand a word of what he is saying. But that's not important, because I'm telling you now what he is saying. He's simply saying that in honor to Galileo Galilei, he has a feather and a hammer, and he's going to drop it from a height of 1.6 meters, and the feather has a weight of 30 grams, and the hammer 1.3 kilograms. None of that you can understand, but you can actually see, if you look very carefully, that indeed when he lets them go, they both hit the surface of the moon at the same time. So, Bill, if you can get this going for us. I need my laser pointer, that would help a little. We're going to make it almost completely dark, but not quite.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named
Here is the hammer and here is the feather. That's the hammer.
Who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place
This is
to
the hammer.
confirm his findings than on the moon.
This is the feather.
And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that?
Thank you, Bill. You may have noticed that it did take longer to fall down than it would have on Earth. You may have noticed that, even though it's not 6 times longer. We'll talk about that next time. You all know what a pendulum is. This is a pendulum. The pendulum has a length L, measured to the center point of that mass that's there. You may want to call it weight, physicists call it mass. And now you can make that pendulum swing back and forth. And you can calculate, and I do that, of course, in my classes, you can calculate how long it takes for a pendulum to make one complete oscillation. So to go all the way from here, come to a stop, and go back all the way here and swing back and forth. And that time that it takes, we call that the period of the pendulum, and we give that the capital T. T is going to be in seconds. T is 2 pi times the square root of L over G. You already know what L is. You have to take L in meters. We all know what G is, 9.80 meters per second square. And if you don't know what pi is, wait until Thanksgiving's Day, and then you will. This is in seconds. This equation that I have derived many times in this lecture hall is only correct if you make two assumptions. And one assumption is that you keep these angles, I call this alpha, that you keep these angles small. Physicists call that a small angle approximation. And another condition is that the mass, m, in here must be way larger than the mass in the string. That's the condition for this equation to hold. If you take that equation and you come home and you put in L equals 1 meter, but you can do with your little calculator, you apply this equation, then you find that T is very close to 2.0 seconds. Therefore, if you make it 1/4 meter, you make it 4 times shorter. Since there is a square root here, the period gets 2 times smaller, not 4 times smaller, but 2 times, because the square root of 4 is 2. So now you get T equals about 1.0 seconds. I want to just show you very qualitatively, not meant to be a precise measurement, this enormous difference. So here I have a pendulum which is 1 meter long. We have marked it here, and I can swing it back and forth. 1, 2, 3, 4, 5. Roughly 2 seconds per swing. Now I make it 4 times smaller, and now it should have a period of only 1 second. 1, 2, 3, 4, 5. Goes twice as fast. Now I'm getting to some real business. In 26,100, we have here the mother of all pendulums. We have measured to the best of our ability how long the cable is and the length of that cable is 5.2 0.20 meters, but we cannot be certain about an uncertainty of 5 centimeters. And I told you earlier, any measurement without knowing the uncertainty is meaningless. And I'm not here to do a meaningless experiment, so I owe you that we don't know exactly the length, but we know the length to an accuracy of 1%, 5 out of 520. So if now I ask that equation, what is the period that you would get with that equation? Then the answer is that t would be 4.58 plus or minus 0.02 seconds. You can check that for yourself. You put in there first for L 5.25, then L is the largest value, then you put 5.15, that is the lowest value, and that gives you then immediately this uncertainty. So I should be able to demonstrate to you that our pendulum has this period. So this is a prediction. But now comes the problem. And the problem is that it's only correct for small angles. And so all my students over the years have always asked, well, what is small? Is 1 degree small? Is 5 degrees small? Maybe it doesn't work at 5 degrees anymore. Maybe if alpha becomes 10 degrees, the equation is totally wrong. So what I would like to do, I would first like to see if we make the angle 5 degrees, whether we can agree with that number. If it does, we can try 10 degrees to see whether the equation falls apart. Now, at 5 degrees, what I'm going to do, I'm going to measure 10 complete oscillations, 10 times I'm going to let it swing, and you will see very shortly why I do 10 times. You would say, what a waste of time. We didn't come here just to waste time. Why don't you just make 1 oscillation and time that? Well, very shortly you will see why. There's a very good reason for it. So 10 oscillations at 5 degrees, and that gives me then a number plus or minus. That depends on Walter Lewis, who is doing the timing. If I slept well, maybe 1/10 of a second uncertainty in my measurement. I have to start it, I have to stop it. If I didn't sleep so well, maybe 2/10 of a second. But it should be somewhere there. I'll tell you a secret. When I first did this at MIT, I was way younger than that. I always told my students, I can do it within 1/10 of a second, and I always did. But now I'm 76 years old. And I'm not sure I can still do it with 1/10 of a second. But probably I can do it better than 2/10 of a second. So I allow myself an uncertainty of 0.2 seconds. So whenever I start and stop, doesn't matter how long it takes, there is an uncertainty of 0.2 seconds. And remember, a measurement without knowledge of uncertainty is meaningless. Why am I doing 10t? Because once we have this number, we're going to divide this equation by 10, and then we get t is a number plus or minus 0.02 seconds. Because you have to divide everything by 10. So this also has to be divided by 10. So now I can determine the period of that pendulum to 2/100 of a second. And that's only because I allow 10 oscillations. You may say, hey, this is also 0.02 seconds. That is a complete accident, because this 0.02 seconds is only because of the uncertainty of 5 centimeters in the length. This happens to come out to be an uncertainty of 0.02 seconds. This is Walter Lewis who makes, call it a mistake, start, stop. If you do it many times, there is going to be a spread in your observations. So let's first do it at 5 degrees, and then see whether we come anywhere near what the equation tells us that it should be. The way I do this, I'm going to swing this. This point here on the floor is 5 degrees. I'm going to let it swing, and when it comes to a halt here, I start it. And I want you to count from 1 to 10. And then, when it stops here again for the 10th time, without looking there, I stop the timer. Is it set at 0? Yes, it is. I may start it after 1 or 2 oscillations, but you will see when I start it. 5 degrees. No! Count. You're very good. 45.79 divided by 10 gives me 4.58 plus or minus 0.02. No need to applause for me, because the equation predicted it. On the other hand, it shows that I could do better than 200th of a second, couldn't I? So now we should continue, because now we want to know whether maybe at 10 degrees the equation falls apart. So we're going to do another measurement at 10 degrees. And again, of course, we will do 10 degrees, we will do 10t, and then we will do t plus or minus 0.2 plus or minus 0.02 seconds. Okay. Here is the 10-degree mark. Yeah! You count. Wow. In spite of my age, I haven't lost it yet, have I? 4584. I will round this down because this is below 5. If you want to keep the 4, be my guest. I don't remove it to have it identical. I rounded this up, I round this down. When I look at that equation, there is something that bothers me. Something that I don't quite understand. And I wonder whether you understand it. Do you see that capital M there? That capital M is not in the equation. Don't you think that if I had an extremely large weight and I hang that at the end of the pendulum, that the period would become much longer because this huge weight has to be dragged back and forth, and so you expect that the period would go up. But the equation says, no, that's not what's going to happen. I'm going to also bring that to a test. But that's a more difficult test. I'm going to hang on that pendulum myself. And I weigh 80 kilograms, and that object is 15 kilograms, so that makes the total 95 kilograms. Now, there are a few problems. One problem is the following. If this is the object, and I would sit down on the object, so this is the pendulum, then, if I do that, then the length of the pendulum is no longer the same that it was before. Because remember, we measured it from here, and if now I put a lot of weight there, of course, that center of mass goes up, and so L becomes smaller, and if L becomes smaller, the equation says that T will become smaller. So, I have to hold my body as horizontally as I possibly can to be at the same level as that object. That's not easy. And second, it hurts. Then I have to time it, I have to start the timer, and I have to stop the timer. But I cannot look at it and say, now it comes to a halt, now I start. I have to do it purely by my senses. When I sort of feel that it's stopping, I start it. And when I later feel that it's stopping, I stop it. To do that with an uncertainty of 0.2 of a second, I'm not so sure I can do that. But I'm going to try. So, I need the switch in my hand. I will start it probably after 1 or 2 oscillations because I want to make sure that I'm in horizontal position. I cannot sit like this because L is now shorter. So I will start when my system tells me that I come to a halt here. It hurts. It already hurts now. Yeah! You count. Can't you count a little faster? Well, I haven't lost it yet. T with Walter Lewis. 45.58 plus or minus 0.2, that means 1T will be 4.56 plus or minus 0.02, which is consistent with all the other values, within the accuracy of my measurement. Within the uncertainty of the measurement, all four values are the same. And so, it is an amazing equation in which I've shown you that even up to 10 degrees it's quite accurate, and even with an increase in mass that is huge, it's doing extremely well. If I move an object with mass m, from location B, which is the floor, to location A, and if the vertical distance between A and B is h, I have to put in energy to overcome gravitational force. And the amount of energy that I have to do, E, is m, which is the mass in kilograms, times h, which is this distance in meters, times g. G is something that we all know what that is. The answer then you get in joules, which most of you are not familiar with. That's the units of energy that physicists often use. There are many units of energy. This is a very common one. So m has to be in kilograms, h has to be in meters, and g is the 9.8 meters per second square. So let's take a case that m is 1 kilogram, and that h is 1 meter. Then E is 9.8 joules. Let's take the same 1 kilogram, and we move it 2 meters. Then E is 19.6 joules. And the higher I bring it, the more energy I have to put in, the more work my muscles will have to do. We give this a name in physics. We call that quantity of energy, we call that potential energy. To be precise, we call it gravitational potential energy. And that gravitational potential energy is the difference between the mass being at A and the mass being at B. So the mass at A is has this much more potential energy than when it is at B. Now, when it is at A, I drop it with 0 speed and I let it go down. What happens now? It speeds up. And we know exactly how it speeds up. There's your equation. It falls down. It has 0 speed at A when I drop it. And so it increases its speed. It goes faster and faster. And it finally hit the floor B. So the potential energy, as it falls, goes down and down and down because H becomes smaller and smaller and smaller and is 0 here. Speed is energy of motion for which we have a name. We call that kinetic energy, and I will talk much more about that on Friday. What I want you to appreciate today is only one thing. And that is when an object falls like this one does, then it can bounce back up. If it is putty, then it probably will not bounce back at all. It will just stick at B on the ground. But in some cases, it may actually bounce quite a bit. So I drop it here with 0 speed, and it came up to here. Now, the one thing that it could never do is to bounce up to a point higher than A. If it did that, then the potential energy with that object here would be higher than it was at A. So when I was watching the ball game on television, I let it bounce once, and I gain a little bit of energy. I let it bounce twice, and I gain again energy. And so the world energy problem has been solved. You don't have to do anything. You keep adding energy out of nothing. So clearly, this cannot happen. This would be a violation of the holiest law of all of physics, which is the conservation of energy. So it is very important that you understand when this object bounces back, it can come lower than A. In extreme cases, it might reach A, but it can never go higher. Now I return to my pendulum. Here is my pendulum. And it's swinging back and forth. I release it here with 0 speed, and I let it come to a halt here, and let it come back, as you have seen many times now. It is not possible that when it comes back here, that it would come a little higher than from where I released it. If it did, it would violate the conservation of energy again, because it would be higher than from where I released it. Because if it came higher, then I go back to my television station, and then I wait until it comes here, and here, and here, and I keep building up energy out of nothing, solves the world energy problem, and so it can never go higher than the point from where I release it. Provided I do it with 0 speed. Of course, if I push it here, if I give it a push and it comes back, of course, it can go higher. That's obvious. We have here on the wall a glass plate. Here's a glass plate. And so, if I take this object, and if I released it here with 0 speed, there is no way that that glass would ever break, because the glass is higher than the position of this object. And it couldn't go higher than it is this. Now, of course, if I gave it a push, that would be a different story. And so I wonder, shall I do that? Shall I give it a push? Who would like to see that indeed, with a push, it would go higher and therefore break the glass? You're just like my MIT students. You want destruction. You want destruction. Now, Bill is going to remove that. Now I'm going to do the most dangerous experiment that I've ever done in my life. To demonstrate to you that I do believe in the conservation of energy. I'm going to stand against the wall so that my head cannot move back. And I'm going to release this object from my chin. And I let it swing. And if I don't give it a push, I will survive. But if I do give it a push, forget that lecture next week. This may be my last. This is no joke. If I gave it a push, it would have major consequences, and I therefore need due cooperation. I don't want you to speak. I don't want you to cough. I don't want you to sneeze. I don't want you to talk. I even prefer that you don't breathe. I'm going to count down from 3 to 0, and I don't want to hear any sound when I let it go. It's touching my skin now. Something you should know. Whenever I do this experiment, I never sleep well the night before. Something else you should know. When I do this experiment, I always close my eyes. 3, 2, 1, 0. Physics works. And I'm still alive. I hope to see you on Friday. Thank you.